Can you see my slides? That's the tricky part.
Yes, we can.
Oh, wow, it worked. Thank you. All right, thanks everybody. So just a little bit about me. My name is Christos Papadopoulos. I'm a professor at the University of Memphis. My specializations is in computer science and specifically networking and network cybersecurity. And my interest in cars is relatively recent. I spent a couple of years with the Department of Homeland Security managing IoT. IoT projects and also vehicle cybersecurity projects. My co-conspirators are Susmin Shanigrahi, who's at Tennessee Tech University, that's in Tennessee, and Alex Afanasiev at Florida International University, and Spiros Thanasoulas, who's also at the University of Tennessee. Okay, I'm not going to dwell too much on this picture because this audience, I am sure, is all familiar with it. The main point that I wanted to make is that in-vehicle networks are evolving rapidly, going from CAN networks to automotive Ethernet. At least this is what I'm hearing, that automotive Ethernet is likely to become ubiquitous. And I am going to make that assumption for now, but the presentation does not depend on Ethernet becoming ubiquitous. So the reasons for why Ethernet is exciting are many. And for this particular presentation, the reason that I like it is that we can actually do interesting things with it, such as provide high bandwidth data, whether it's from cameras or from IVI systems, but also provide security. We actually have enough payload to do authentication and other interesting security things. This one, again, I think the first statement at least should be pretty familiar to this audience. CAN doesn't have security is a little difficult to add because of many reasons, but perhaps the most dominant one is that the payload is just so small, and it's very hard to add authentication headers and other information that you need for security and authentication. With the advent of automotive Ethernet, the automotive industry has been looking at the IP stack, or the Internet Protocol stack, as a contender for automotive networks. And there's a good reason for that. This is ubiquitous Internet technology, and we have decades of experience with it. We have standards, we have maturity, we have code bases, is just there, and it seems to work at the internet. On the security side, we have a number of security protocols available at different layers, and MACsec, IPsec, and TLS are two that come to mind. So what's not to like? Well, if you talk to internet security people, the thing that they will tell you about security in IP is that it's notoriously brittle and complex. We're still facing issues such as authentication, distributed denial of service or plain denial of service, man-in-the-middle attacks, spoofing, replay attacks, and so forth. And the reason is obvious. IP was never designed with security at the start. Security was always an add-on. And whenever you add things on to any system, then things become a little clumsy. Already, the use or the potential use of IP in automotive has given rise to work such as intrusion detection systems, CAN security, authentication, and more. Another testament to the fact that we don't have security built in with the IP stack. Well, is the adoption of TCP/IP inevitable? And depends on who you're talking to. Sorry about that. Let me go back. So several studies, and some of them that I've seen at DHS, they claim that it is very likely. The question we are asking, however, is that should we blindly go into IP and adopt all its features, including its limitations? We believe that before transitioning away from CAN and into IP, the automotive community should at least look at the alternatives the alternatives to IP, I mean. Then there are some that offer better communication models, better security and interoperability, and also simplify applications. We believe, and this is what excites me about the work with VSS, we believe that VSS can be leveraged to add security to the network technologies that adopt it. I think everybody knows what VSS is. I don't need to describe that. And I think everybody knows what VSS is intending to do. The claim that we have here is that VSS, coupled with the right communication architecture, can be leveraged to secure vehicle communication. So the question is how? Our answer to this is by using a new network architecture that we call Named Data Networking, or NDN. A little bit of a background about NDN. NDN was originally funded by the NSF back in 2010. It was one of 3 future internet architecture projects. And at the time, it was funded at the tune of about $7 million. Of the 3, NDN is the only one that is still active today. And NDN actually went on to get funded on the second round of funding, which was another $7 or $8 million. And then with that, and with other funding that came from individual projects that use NDN, today we have over $20 million worth of funding. And I think my collaborators might claim that we're closer to 30. It already has a large community of developers and users. We have a global testbed with about 40 nodes that's deployed as an overlay over the internet. We have annual community meetings that are hosted by NIST, or the National Institute of Standards in Washington, D.C., for those who are familiar with it. There's several papers, a lot of them appearing on the Information Centering Networking, or ICN conference. And we've even had adoption by various commercial applications. I'll give a link to where you can find information about NDN in just a second. So the question we're asking is, can we apply NDN for in-vehicle networks? Because NDN, as I mentioned earlier, was originally developed to be deployed over the internet. And since I'm here, you're probably guessing that the answer is yes. Why should we consider NDN for in-vehicle networks? And I will give 3 high-level reasons. One is simplicity. NDN has only 2 types of messages, a message called interest and a message called data, and I'll explain those in detail. NDN has no endpoint addresses. So there's no IP addresses with NDN. It's all content-based. And by eliminating IP addresses, you no longer have to worry about IP address management, and you no longer have to worry about name resolution. In other words, you make DNS obsolete. NDN offers scalable forwarding through hierarchical naming. And this is very similar to how IP forwards packets. If you're familiar with IP addressing and forwarding, IP forwards packets based on longest prefix match, and this is how you can do traffic engineering, and you can forward more specific addresses to certain routers and certain networks. NDN has efficient delivery through stateful forwarding. This is different than IP. IP does not have stateful forwarding. NDN has in-network caching, and it offers native multicast. NDN offers security that IP does not. Because NDN is name-based or content-based, and content is first-class citizen, then all content in NDN is, when it's produced, is immediately signed cryptographically. So everything of content along with its signature, and that becomes the unit of communication in NDN. By doing that, the content is verifiable, tamper-proof, and immutable, because anytime you receive content, you can immediately validate the signature and determine whether the content that you received is actually the content that is associated with the name that you asked for. And that's important. I'll come back to this concept quite a few times. NDN also offers interoperability. It has common methods to publish, locate, and retrieve content. You only need to agree on naming. And coming back in a circle, this is where VSS comes in. Because with VSS, what is VSS? VSS is an agreement on naming at some level. And this is all that NDN needs in order to communicate. So this is the network service model. In IP, this would look something like, give me an IP address, I resolve give me a domain name, I resolve to an IP address, and I will take you from one machine to another. Now, in order to retrieve data in IP, you have to locate the server or the IP address where the data is sitting, find that machine using DNS and IP routing, get to that machine, and then ask for the content. For example, ask a web server for the content that you want, and then have the web server deliver it back to you. The problem here is that IP is channel-based, is path-based, or however you want to describe it. IP only cares about getting you from one machine to the other. It does not give you the content that you want. This is something that you have to build on top of IP. In contrast to IP, NDN, the service model in NDN is, I give an interest to the network. In other words, the name of the content that I want. We also call it, I ask a question to the network, and I get back data. So no more resolution, IP addresses, and so forth. I tell the network the thing that I really want. If I were doing this in the web context, I would give the network the URL of the page that I want, and then the network will bring that back to me. Now you might say, we'll already do this. I mean, this interface is a middleware that will do this for you. The key difference here is that we do this at the network, not as middleware. The network itself accepts names and delivers content. And for those who may be familiar with the IP hourglass design, this is what NDN does to that concept. So on the left, we have the representation of IP. And what this means is that IP was the first protocol that was end-to-end. In other words, it connected all machines on the internet together. This was the means to create a global network. With NDN, we use content as the means to connect all the networks together. IP gets actually pushed down and becomes another link layer. But right now, the face of the network is content. And this is what NDN is trying to do. Your interface with the network is content. All right, so NDN, you may have already guessed that how naming in VSS and NDN may begin to interact. So NDN leverages VSS, and let me give a very simple example for the value, the VSS value /vehicle/chassis axle row 1 wheel tire pressure. And I know VSS represents this as dots. In NDN, we use slashes to separate the various components. So this value, this name rather, not the value, now becomes an NDN interest. And this is what I would ask the network. I will deliver this to the network when I want the tire pressure, that particular tire, the value of that tire pressure to come back to me. And the network will return a data packet to me with the value of the what I asked for. As a quick aside, CAN is also a name-based network at some level. And I find it interesting that NDN is also a name-based network. And I wonder if that makes things easier for developers to go from a CAN mindset to an NDN mindset. Okay, so how does this all work? Now, I'm going to get into the details right now. But I think the details are very easy, and I have a few diagrams that you can follow. So the first thing that needs to happen is a vehicle ECU needs to advertise the name prefix for content that it can serve. And I'm using toy examples here, and these may or may not correspond to real life, but these are for illustration purposes. So as an example, we may have a chassis ECU in the vehicle, and under VSS, the namespace under the chassis ECU will start with /vehicle/chassis. Now in NDN, this becomes the prefix that I advertise. This is what the chassis ECU will tell the network that these are questions that it can answer. So what this means is that any question, any interest that is sent into the network that starts with /vehicle/chassis, and it doesn't matter what the rest of it is, these are questions that the chassis ECU can answer. And what it tells the network is, if you see a question like that or an interest like that, then send it to me. I'm willing to answer it. For those of you who are familiar with IP, this constitutes the network portion of the IP prefix. And in our case, is the network portion of the name. The NDN forwarders, these are analogous to IP routers, but obviously they have NDN functionality. They receive this prefix, just like IP routers receive IP prefixes, and they store them. And the other thing they store is the interface where the prefix was received from. And the idea is that if I receive a prefix from a particular interface claiming that it can answer these questions, then if I get questions or interests that are asking the questions with this prefix, I send them out that interface. So NDN sends interests with the signal name, and here's an example, again, our tire pressure example. And NDN will route the interest to the nearest ECU that advertises /vehicle/chassis. And I know that it doesn't have to be just one. Think back to the discussion we had earlier about questions of about engine speed, and the question that followed that was which engine speed. You can have multiple devices providing values for these signals. Then the chassis ECU, once it receives this question or this interest, will respond back with a data packet. It will include the name of the question that it is answering, and it will also include the value. So in this case, it will tell us that the tire pressure is 35 PSI. So here's a picture showing the prefix advertising, depicting what I just said earlier. So we have the chassis ECU on the right. It sends the /vehicle/chassis advertisement. It goes into the network. The domain controllers here are the NDN routers, or the NDN forwarders, as we call them. They receive the prefix, they save it, they note the interface where it came from, they forward it to their neighbors. And this way, the prefix gets distributed in the network, and everybody knows how to route interests when they come to them. All right, the other interesting thing about NDN is the stateful forwarding. So when an interest reaches an NDN domain controller, or an NFD, it leaves behind state. We call this the pending interest state. So when the question /vehicle/chassis and so forth goes through NFD, NFD remembers that somebody asked that question before it forwards the interest to the ECU that sent out the prefix advertisement. If a similar interest arrives, then it doesn't get forwarded. The incoming interface, if it was different than the one we received earlier, is simply marked. And when the data packet comes back, then the local NFD remembers that there were two interfaces that asked the same question, copies the packet, and sends them out to both. In addition, when a data packet arrives and answers a question, the domain controller remembers the answer, or it caches the data and saves it locally. This is something that IP cannot do, because IP has no idea what content is in the network, and there's no reason to cache a packet because you can really identify the application or the content, so there's no need to do that. The result of caching is that if future interests arrive for the same data, the domain controller can serve them from the cache. And you might say, well, wait a minute, what if that data is old? Well, what NDN does is to provide an attribute to the data or a lifetime attribute that says that the application decides. And the application, for example, may say this data is valid for this much time, so many milliseconds or microseconds, if you like, at which point it will be removed from the cache. The result of all this is that NDN delivers content efficiently because future requests come from the nearest cached location, and it also implements multicast natively. So let's take a look at that. So here's how interest packets get routed. So here's an ECU on the left, sends an interest packet, and then that gets forwarded and received by the chassis ECU. And remember that the domain controllers remember where this interest came from. And here's a data packet that gets returned from the chassis ECU with the appropriate value. And as it flows through the domain controllers, it gets cached, and then it reaches the ECU that asked the question. And again, I'm reminding people that there's a lifetime here to control the lifetime of packets in the cache. And also remember that these packets are digitally signed. One convenient result of this is that if you have retransmissions, if a packet is lost and you need to retransmit it, then you send a retransmission request, and the retransmission will come from the closest domain controller who has the data in the cache. This one shows the interest aggregation, which is what I described earlier. If an interest comes for the same data, then the domain controller doesn't have to forward it if a pending interest is already in place. But even if the interest comes asynchronously, in other words, after the data was delivered, then that second interest can retrieve the data from the cache, assuming it's still valid. And this is what implements multicast functionality, but unlike IP, this is asynchronous multicast functionality. Okay, and this is what this one is showing here. Okay, in the interest of time, I'm going to skip the details on how this is implemented. They will be in the slides and everybody can see them. The only thing I would point out is the forwarding strategies that are in NDN. And these are strategies that are local on every router. And what they do is they apply specific behavior for specific namespaces. For example, if you want a specific data from a specific namespace to get priority, then you would implement it in the forwarding strategy. If you wanted to implement something that is time sensitive and you needed strategies at each router to ensure timeliness, you would put it in the forwarding strategy. Okay. I believe, based on what I described, I believe people can follow the what is going on here. So I'll just leave it in the slides for you guys to examine at your leisure. Okay. Let me touch on security very briefly, because I think this is an area where NDN and VSS can really excel together. So NDN digitally signs all packets using the publisher's private key. So the result of that is that content and name are cryptographically bound. So as I said earlier, once you receive content, you check the signature, you know you have the right content. And this is really what allows you to cache data in the network, and you don't care where you receive it from, because anybody can serve it to you. And as long as the signatures validate, then you know you have the right content. You cannot do that with IP. You only secure the path. So you only trust data from the other side of the channel that you have secured. Let's not talk about whether the content was tainted on the other side because somebody broke into a machine. You would not know that you're getting tainted content. You will accept it because it's coming from the other end of the secure channel. You have to add additional functionality to do that. So this eliminates replay attacks if you use sequence numbers, because nobody can tamper with them, but if they do, you will know. What it enables receivers to not accept fake data. What is still possible is interest floods. So in other words, I can no longer attack you by sending unsolicited data packets to you. The whole interest data combination turns NDN into a pull model. In other words, I do not receive data unless I ask for it. However, I can still get attacked by being flooded with questions, with interests. However, the fact that we do stateful forwarding means that a router in the middle can detect whether we have interests that have been unsatisfied. And that could be an indication or a flag that there's an attack going on because there's a lot of questions being asked, but there's no answers. And as a publisher, as a provider of the data, all you have to do when you're under attack is to stay silent and let the network figure out that there's something, there's an attack going on. Keys can also be distributed as content, so they're under the same protection as data. And we have some techniques where signature keys can be delegated. There's a lot more detail on that, and that I don't have time to go in this presentation. But key delegation reduces the risk from compromised keys, and they're used as a basis for something we call trust schemas that I'm not presenting here, but I'll be happy to go into another presentation. The result is that NDN standardizes security at the network layer and provides a strong foundation to implement application-specific security. So briefly, what does NDN offer VSS? Well, VSS provides the naming structure and NDN provides the transport. So now, with the combination of the two, what it means is that if you publish your data under VSS, then you can employ NDN to gain transport. So now you have also the means to transport your data in the network. And I think this is a great incentive to adopt VSS. In other words, all you need to do to ensure your data can be transmitted in the network is to publish it in VSS, and then just use NDN. NDN provides efficient delivery. We talked about caching. We talked about asynchronous multicast. And it can also provide things such as seamless failover, and redundancy. For example, think of having multiple ECUs providing the same data under the same name in the network. NDN doesn't care where the data is coming from. So if one ECU goes down and no longer answers questions, another ECU could be up, and it could be up at the same time. I mean, you could advertise into the network the same prefix, and there'll be a seamless failover without the consumer, the client, having to do anything to switch over to a backup or anything like that. And of course, it provides a foundation to build robust security. Very quickly, some related work. SAM-IP and DDS come to mind, along with other pub subsystems. At the high level, these have a similar functionality with NDN, but the fact that they still rely on IP means that they're susceptible to IP security vulnerabilities, and you still have all the overhead to set up and manage IP addresses, along with the other disadvantages that I pointed out. The current state of NDN, it is code-based. This code base available, is actively maintained. We've got multiple versions of NDN in C++, Go, Python, and so forth. I talked about the testbed. We've got your usual collaboration features, such as Slack and mailing lists and so forth. And there's a lot of tutorials, presentations, papers, and project descriptions on the namedata.net website. And we've already applied these to applications such as IoT, delivering climate data, high energy physics, genomics, and so forth. So let me wrap up very quickly. This is, again, meant to summarize NDN. The picture on the right shows a simple testbed that we're putting together with Raspberry Pis, where we're deploying NDN and trying it out with various automotive applications. But let me touch on limitations. So while NDN is mature, it is still an experimental architecture. We have no standards, there's no hardware implementations yet, and so forth. And maybe that's not a bad thing, because we want NDN to mature to the level where somebody can take it and put it in hardware. Only mature technology typically goes into hardware. And future work will continue integrating VSS into NDN and hopefully demonstrate these with various testbeds. And let me acknowledge Glenn and Ted from Geotab for introducing me to this group, and Joby and Paul for making this presentation possible. My apologies. I think I ran over with a few minutes.
You actually have 7 minutes.
Do I? Okay, good. Then we can maybe have a discussion.
Yeah, we have a couple questions here. It looks like from Ibrahim, is NDN architecture the same as broker submit and purchase in IoT and MQTT?
I think it's not the same. It's very different, because I'm not familiar with the broker architecture. I'm familiar with MQTT, this is a queuing system. I think the comments that I made earlier, that there's a number of other architectures that rely on IP. I think this is the main difference. So NDN is again a content-based, name-based architecture. I believe the other architectures build on top of IP. So they develop functionality that is similar to NDN at the end from an application point of view, but they still have some of the disadvantages that IP does.
Let's see here. I'm not sure if what Ziv had was a question or an answer. Ziv, is that a question? Do you mind unmuting and asking if it is?
Yeah, it was sort of a statement and partly a question. So basically what it solves is really ensuring that you secure the channel, let's call it end-to-end, so you know that the transmitter of the information is really the valid transmitter. But there's still an open question whether this transmitter was compromised or not. So the validity of the data itself needs another layer this way or another.
So let me clarify. Let me clarify one thing that you said. So we do not secure the transmitter. This is what IP does. We secure the content. So in our case, we don't care who the transmitter is. It could be the entity that generated the data, for example, an ECU that generated the data. It could be a repository. It could be a cache in the network. It could be anybody else. And what we secure is the content. So I don't care who it is who gives me the content. What I care is, once I receive the content, is that the signature validates, and then and only then I can trust the content. So for, you mentioned compromised and breaches. The way to compromise data with NDN is to steal my private key. Because as long as my private key is guarded and nobody has access to it, and then the person with the private key signs the data and then puts it into the network, then I honestly don't care who got compromised. As long as I got the data and it validates, then I trust the data. Does that make sense?
Yeah, well, what I maybe aimed to be more precise. Let's say we have the TPMS sensor, right? So when this sensor sends data to the network, you know this is the actual right TPMS sensor because it's signed by its private key. On this, we fully agree. Nobody can, let's say, steal the private key, and nobody can impersonate to be this TPMS sensor. But what I mean is, since the TPMS sensor itself is using a wireless technology, even somebody might compromise this sensor and then just run code on it and send invalid data into the network, which will obviously be signed properly. So I think there needs to be another layer of security, ensuring that whatever is being sent also makes sense and not just signed by the proper component.
I completely agree with you. My claim is that that job, that functionality does not belong to the network. I think that is something that needs to be built on top of the network, because it's applicable not only for applications running over NDN, but applications running over anything. I mean, securing your public key is basic security hygiene, you need to figure out how to do it. So there's nothing here, there's nothing in NDN that hurts you in that particular case. I would claim that there's actually things in NDN that might help you because the symmetric transmission, for example, and the fact that you have visibility to the content name in the network, you can use that to detect patterns that correspond to a compromised activity. With IP, you're completely blind to that. So with the TPMS sensor example you mentioned, if somebody compromises the device and tries to send me crazy tire pressure values, I can even put that in the first NDN router, who sees the content, sees what the name says, sees what the value is, and I can maybe put it in as a firewall, something that says if you receive content from the TPMS device with the TPMS prefix, then do a basic range check. If it claims that it has 2000 psi, then don't accept that.
Yeah, fully agree. Sort of a distributed IDS.
Yes, but it's the fact that now I have visibility to the name of the content that allows me to do that. And that's another advantage of using names in the network.
Yeah. Thanks a lot.
All right, I see a response in chat. Dilab, was there any question in there, or is it just a response back in chat?
No, this is just a response. I fully agree with the assessment, and we need a multi-layer defense in this approach. You cannot rely on one thing, and having a secured channel is important, obviously, but eventually we need to make sure that the content is valid and makes sense and is plausible.
Right.
This applies, for example, for V2X, which is a different area in which life becomes much more complex because it's not one network, it's an external network. But going into the in-vehicle, definitely a protected channel plus content inspection is a good approach.
Perfect. Any other questions? We're going to take a short 5-minute break, and then we're going to come back at 5 after the hour. So any questions now before then?
One last comment if there's no questions.
No, you're going ahead.
Okay, very quick comment. So I wanted to emphasize that with NDN, the distinction between network and storage is now blurred. So what I mean by that is if there was data that was static and I wanted to have access to that data in the network, then I can stick a USB drive on the network with NDN activity, and that itself can respond to questions, right? I can blend IP networks, Ethernet networks, Bluetooth networks. NDN doesn't care what type of network you have underneath. All it cares is that the two ends agree on something to allow them to talk to each other. And using these different link layer technologies with NDN becomes seamless. Which is, I think, is another advantage in automotive networks where we expect multiple types of networks to coexist for at least a while.
Sure. You can still take a break, folks. We have one other question here. And I think we somewhat answered it earlier, but this is from, sorry if it's incorrectly pronounced, but Elon. Is the NDN, in the NDN can keep end-to-end encryption for data in rest and use / transmit?
Yes, so encryption is something that is functionality that you build on top of NDN. This comes on the confidentiality aspect of NDN. And so obviously, if you want confidentiality, you need to encrypt. This is the only way we know how to do this. What NDN allows you to do is, with the security features that it has, it gives you the ability to do key distribution a lot more efficiently. So for example, if I want to share keys with a group, then I can use the underlying security features of NDN to distribute those keys securely. And there's a lot more to say about that.
Yeah.
Happy to get into it when we have more time.
And just a quick question, is your contact information if people have questions for you? Is your contact information in the slides? Like I said, we'll share slides in the next couple of days. So.
Oh, maybe I forgot to put my email address. I will put my email address on and send you a new version, Joey. Sorry
there you go.
that.
So anyone else has any questions, you can reach out to Dr. Christos. Yeah, no, I understand. And he will be able to provide some more insight to you because I'm sure there's a lot more to say there. So thank you so much. And we'll be back in just a couple minutes, folks.
Thank you.